Greetings, the Astro 30 here yet again, looking at what is going to be for a while a final video on series pass regulator experiments. Now, I've gone ahead and from the previous video before the last one, I looked at an error amplifier where you could adjust the voltage by adjusting the feedback to the error amplifier. Well, this is fine, but it's not really all that stable output wise. So I've reconfigured the circuit and I'm now using any 5534 ICs. They have a maximum supply voltage rail of plus minus 22 volts. So that's 44 volts across pins 8 and 4. So that means I can pump up to 35 volts DC into the main supply rail. And if the negative 5 volt rail, or the negative rail I should say, is less than negative 5 volts, that still keeps us within the range of the absolute maximum ratings of this particular IC. So I've gone ahead and tested everything at 15.6 volts for now. But first I'll show you a schematic, and I've split them up into modules to make them a little bit easier to follow. And then we'll come back and do some tests. Okay, and here is a look at the schematics, and as I said, I have split them up into 3 separate modules just to make it a little bit more clearer in demonstrating the schematics, so it's not all convoluted all on the same page, if you get what I mean. So anyway, we've got our 24 volt AC and 0 volt respectively coming off the secondary of a transformer. Now that's what I'm planning on running it at. I might actually include a 3 amps fast blow fuse, or maybe less than that, 2.5 amps fast blow fuse here on the secondary, just to protect the transformer from any accidental overcurrent conditions at lower voltages. Say that this was able to deliver 5 amps into a 5 volt load. We don't really want the transformer going away because that's more expensive to replace than a fuse. So that's one thing I would do. You just really have to watch what you're doing. So this is the current limiting circuit. It's the same as I've just demonstrated in a previous video. It's just a comparator using an NE5534 now. 10k linear pot. Don't use any value higher than 10k or the circuit will not operate correctly. And as I've explained in a previous video, it just samples what the voltage drop across this shunt resistor is compared to what this comparator's input voltage is set to. Once they equal the same, or this one down here goes higher than what this preset limit is, then this will clamp down to the negative going rail of the op amp, which is in this case it's negative 3.3 volt. Now I kept it at negative 3.3 volt just to keep this op amp under the absolute maximum ratings of the supply voltage, which is 44 volts across pins 7 and 4. So once that comparator slams down to the negative rail, we sample that negative going output off to our limit point and turn on a PNP transistor to drive a constant current LED. So this is the voltage amplification stage and error amplifier. This was also explained in a previous video as to what it does. In this case, I'm operating this at around a gain of 15, set by this 68k resistor and 4k7 respectively. That just allows the input here, which is only going to be a maximum of 2.5 volts, to be amplified up to our required output voltage. And it does work pretty well, and it is pretty stable. Testing it at a higher supply voltage of 30 volts on this VCC rail to see if we can get up to the full voltage would be another thing, but we'll do that in this video as well. I also found that by adding a 1k resistor to the emitter of the driver transistor and this output of the Darlington stage here,
made this stage much more stable. And this diode here is just our back EMF diode for back EMF that might be present on the load side, so it's not going back through the transistors and destroying things. This is what also that diode is for. It's also a protection diode. So the differences with this circuit is I've now moved my voltage set point from setting the gain to actually controlling the input pin. So here is our LM336 2.5 volt voltage reference source over here, which can be trimmed out to give us exactly 2.5 volts. And we go from 0 to 2.5 volts on this input. This amplifier will amplify that, and the resulting output will be anywhere between 0 and, well, in this case 30 volts. This 100 picofarad capacitor is very important, going between pin 6 and the inverting input of the op amp, because if it's not present, I found without it, that say you set the output voltage to 3.3 volt and then you load it with, say, even 330 ohm or even 22 ohms, the voltage would have shot up to actually to 5.5 volts, so almost 2 volts higher. And the same at 5 volts, drive up to 7, and that is totally unacceptable. So this capacitor helps keep that op amp stable, and so that it's not giving us spurious output voltage differences compared to the load dependency. The limit from the last circuit comes into here and can go to the base of the BD139 driver transistor to still base current, or it could simply go into pin 3 directly here, and the result will be exactly the same. The voltage will start being clamped off. And just to keep things complete, this is our negative 3.3 volt generator circuit. I've explained this in a previous video before. We've got here a series pass regulator circuit, which is set with an error amplifier here with 2 equal resistors on the resistive divider here, which will give this roughly a gain of 2. So if we have a 5.6 volt Zener down here, the output corrected here would be about 12.2 volts roughly, and that's also correcting for the emitter to base junction drop of this transistor. And I found you could load this up to 400 mA before it would start loading down and the voltage would start dropping off. So that feeds a 12 volts power supply all the way out to this NE555 timer, which is configured as a square wave oscillator running at around 3.3 kilohertz. We then sample the output, we get rid of the positive going cycle, and we only look at the negative going cycle, which will be around about 10 volts here. And then we smooth it a little bit, and then through this shunt regulator we regulate it down to the required negative 3.3 volt that we want. This 12 volt connection can then bugger off to a VA meter or the load switching circuitry, which is not shown on here for completeness, because I'm considering, when designing a PCB for this, just to keep it simple so it's versatile, have a 12 volt output, and then you can then power another circuit board which does all the VA meter monitoring and load switching and all that sort of jazz, just to keep the circuit and the circuit board small and more concise.
Alright, so we've looked at the schematic, and I think by varying the voltage reference coming in to the error amplifier and just amplifying the signal to give us the output voltage is a better solution, and I found it's more stable. So I've got everything set up. Meter is measuring what's coming off of the output, and I've got my other supply here set to 3.3 volt. That's supplying the negative voltage rail to pin 4 of each IC, and this one over here is still set to 15.6. So currently I have the voltage pot on this experiment set to around 5. So we'll turn that on and the negative rail on. As we can see, we've got 5 odd volts there. Now I've got a 22 ohm resistor as a load there. So if I connect the resistor across the circuit, as we can see, the voltage only jumped up in this instance by about 15 millivolt or so. I'll disconnect it. See, so it is actually keeping the voltage relatively stable. So now if I disconnect my load and I increase the voltage now to say 10 volts, too far. I must admit, having the voltage pot at the input of the area amplifier is a lot more smoother than at the output. Now, I've got 10.2, take the load. Now, it dropped down only because current limiting has come into effect, so I'll turn that off. And I'll repeat that. So 10.2, 10.22. So it only came up by 20 millivolt. That's not too bad. And we're drawing about half an amp off the other supply. That's fine. So if I come up to now 12 volts, thereabouts, there we go, connect the 22 ohm load again, drops down to 12.014. So we're losing about 110 odd millivolts thereabouts. This makes sense because if we connect the load, we're up to 600 milliamps of current draw thereabouts. We're getting to round about where the maximum supply input voltage is, and so the output stage is now starting to fall out of regulation because it's coming close to its supply rail, and the op amp can only swing within 2 volts of that 15.6. Because if we look at the maximum voltage output, which is 14.3, so the input voltage is 15.6, so we're losing 1.3 volts to start with. That's mainly only because the op amp cannot swing to the supply rail. So loading it down now at this voltage, we drop down to 12, so we've lost like 3.5 volts now. But we're drawing 600 mA, and current limiting is not happening at the moment. So with the current resistor values for the current limiting section, I've got 100k there as I stated instead of a 68 that's on the schematic. I managed to get the total current draw on this circuit down to 1.8 amps, so I can't talk this morning. If I short the output, current limiting came into effect, so I'll make sure that that's set to maximum. 1.9 amps thereabouts, and the voltage, it's hot, and the voltage buggers off to 1.2 volts. Okay, so we know that using that 100k in its current configuration, we get almost 2 amps of constant current, which is probably going to be about right. So the next thing I want to do is I want to hook this up to a mains transformer that can produce 24 volts into the circuit and see if it still behaves. I'm still going to use the 3.3 volt supply to give us the negative. I haven't built up the NE 555 timer circuitry to generate that negative rail, but I'm assuming it works because I've used it before. So what I need to do now is find a transformer and a power supply module to give me the DC, and I need to reconfigure the circuit to incorporate that. So I'll get busy doing that and come back.
Wait, your biggest stickers, here's of this.
Okay, I've got a mains transformer wired into this power supply module. Now it's wired across as a complete transformer of 24 volts. So I'm going from one side of the 12 volt winding to the supply, 0 volt side of this winding going to the 12 volt winding on the other side, and then the 0 coming off to the circuit. In fact, I'm going to double check that. No, I've got it wired to the 15 on this side. This is why it's always a good idea to check stuff before powering up a circuit, because that wouldn't have been 24 volts. That would have been more like 29, which would exceed the power rails of the op amps. Anyway, I've got DIN bulb hooked up to the transformer's main as input, so I can see if it's drawing too much current. Also gives me a handy power switch to quickly turn it on and off. Now, doing this sort of experiment with live mains is dangerous, so I will stress here that if you're doing something similar at home with what I'm doing, you're doing so at your own risk. So first I'm going to turn, well, the negative 3 volt reference on so that it's not suddenly getting power through the circuit from the main supply. And I'll turn the main supply on and watch both the dim bulb and the meter. Nothing appeared to happen. Okay, we've got no power to the supply. Okay, well that's annoying. I was messing around with the dim bulb the other day. I thought I had some incandescent bulbs I could put in there, and then I realised I'd used an E27, not a bayonet. So I'd unscrewed it. See if, because it is plugged in, see if we get power now. Nope, diddly squat. Okay, so I've got to fault find why there's no power coming into the mains. Because the bloody neutral wire came out the terminal block. Alright, see if I can fix that. It's so annoying. I should have really tinned the wires on the end of this transformer. Because, yeah, it's not gripping the strands of the wire properly because, well, it's not tinned. So they pull out very, very easily. Right, see if I've got power now. No, no power. Well, that's kind of depressing. Okay, I'm going to have to look at this a little bit further. Much better. There was no AC coming through the bulb because there was a bad connection in that socket. This socket is really annoying the piss out of me now. The LEDs on the supply lit up and I've disconnected the main breadboard circuit from it. And I connected the multimeter across the DC output so I can see exactly how much voltage we got there. We got 31.1 odd volts. So that's fine. So I'll just turn that off. So I know that's safe to hook up to the circuit. So what I'll do is I'll rehook it back up to the circuit and try again. With the PSU hooked up to the circuit, it's starting to bleed the capacitors off. So I'll turn the 5 volt rail back on. So it looks like it was doing something. Right, we got negative 1.7, then that's only because of the reference voltage now. So this is a big moment of truth. I'm going to turn it on, and if anything happens, like the circuit explodes or smoke starts pissing out, then it's an epic failure and it's caught on camera. Hopefully that's not going to happen. So turn the DC supply on. Nice, we're at 4.9 volts, which is roughly where I set it. So immediately it's doing what it needs to do. So I'm just going to monitor that for a while and make sure that nothing's smoking. I was going to do something else, but I can't remember what it was. So I'm going to see if we can still get down to 0 or whether that adjustment needs readjusting. Yeah, it needs readjusting. So I'll quickly re-zero that. There we go. So far, nothing appears to be happening. Put that back up to the 5 volt where it was, and then we'll see how far this thing can go. I reckon the voltage is jumping around a bit because it's still going through the dim bulb. So I'll hook up the 22 ohm load. It just increased, not much really happened. Okay. So I'll wind this up full. There we go. 28.8 volts coming out and everything still looks happy. There's no magic smoke coming off of the breadboard. Can't smell anything getting hot. So I'm not going to do any short circuit tests at the moment because I don't really want to destroy anything. But I do want to do a current test. So, well, I can short it, I suppose, if I put that to 0. Seems fine. Buggers off down to nothing. There's no smoke coming off. Everything looks happy. Okay. So I need to do a current measurement test. See how much current is being limited by the comparator. So I'll hook up that 1 ohm resistor there at 1 volt, 2 volt and 3 volt, which should be a respective current of 1 amp, 2 amp and 3 amp. And I'll put another multimeter in series with the resistor in the output just to measure the current. Alright, I've got another multimeter in current mode. This can be stressful on the meter. It's better to measure across the shunt resistor. However, I'm measuring the output directly in series with the resistor, and it's not connected right now. So I'm going to hook the resistor up, the 1 ohm. We're set to roughly 1 volt, as the other meter confirms, and I'm going to use that to also monitor what drop in the output voltage we get when we start drawing current. So the current limiting pot is at its maximum setting. Okay, and according to what I can see, 1 ohm at 1 volt, and it didn't drop that much, is only drawing 540 mA.
I just want to stop here for a second just to make a point. Ohm's law does not lie. The mathematics always works. Now, if we have a 1 ohm resistor and we have 1 volt of voltage going across that resistor, we should have a current draw of 1 amp, not 500 mA. The meter is saying 500 mA, which is incorrect. Now, I've measured this 1 ohm resistor and it is pretty close to 1 ohm. So why does the meter say 500 mA? Well, my conclusion is the meter is wildly inaccurate, for whatever reason. This piece of information will become relevant in the next few minutes.
So now I'm going to disconnect the load, and I'm going to up this to 2 volts, which theoretically should have been 2 amps. And, well, the dim bulb started glowing a lot brighter. We're at 1 amp on the meter, but the dim bulb has started current limiting. The output voltage hasn't dropped too much. So yeah, the other thing is the limit LED has come on here. So it's, yeah. Alright, so I'm going to disconnect that. I'm going to turn off that supply. What I'm going to do is I'm going to take the dim bulb out of the equation so that it's going directly to the line, because I'm pretty sure that it's safe to connect directly to the mains. I've disconnected the load, so I will replug in that. It reset my meter for whatever reason. Okay, I'll reconnect my 1 ohm resistor. Right, well, it's jumped up to an amp, over an amp, but the limiting LED has not come on, so the dim bulb was stealing a bit of the current. So I'll up this now to 3 volts. I just want to see where the current limiting reacts, and I'll reconnect the load. We're at 1.5 amps now. Okay. So I'll jump up to 4. We're at 2 amps now. Okay, so I'll jump up to the 5 volts, which is where I was. That should be close to 3 amps now. And current limiting has come into effect. So we're at 2.5 amps. Back that off till the... Ooh, smoke just came off of the secondary. I think I have blown that winding. Oh, that's a shame. Well, apart from destroying the transformer, what does this mean? Well, it means the circuit does work, but it'd probably be better to limit it to 2 amps on a 3 amp transformer, just so it keeps it happy. I am going to test the output of the transformer. I have a short circuit between the 12 volt winding and 0. However, 0 and 15 is fine, and the other side is fine. What I have to do is put the transformer on the dim bulb itself and see if it starts drawing excessive current. Alright, hooked up. Doesn't appear to be. Although the transformer is unloaded, so it shouldn't be drawing any current. So I think I've killed that transformer. I will hook it up to the DC supply, but only from the 15 volt to the 0. Okay, I've got the transformer hooked up to one secondary side on the 15. Nothing. Put it to the other secondary side. Nothing. I'll do an AC output test instead. Power supply is disconnected. Well, we've still got 13 and 11 volts roughly there on one secondary. So let me just turn that off, and I'll change to the center tap, where the smoke came out of. That's definitely dead. Okay, let's check the other secondary. 13.8. So the 15 volt windings on the transformer are still fine. So I think I've actually killed this because something did snap over here as well. I think I blew the bridge rectifier because there's no DC going through it anymore. So that's something to look at later. Alright, well I know the transformer's still working apart from the 12 volt winding here. Okay, well I stress tested it, it went up to 2.5 amps, then blew the transformer. Okay, so what does it mean for this little circuit? Well, it works. Just got to watch the current that it draws. And it shouldn't be doing anything strange. I don't know how accurate my meter's current measurement is. It could have been exceeding 3 amps. I probably put 4 amps into the load. Because at 5 volts into 1 ohm, it should be 5 amps. That's what the math says. So I think I've just exceeded the current capabilities. So what I'm planning on doing is making a PCB for this. Now I want some suggestions. Should I include all the load switching, meter output circuitry on this new PCB as I did on this one, or should I make it a little bit more universal and versatile by just having a 12 volt output from the series pass regulator that drops the main VCC down, and then leave it up to the constructor of how they want to use that 12 volt rail, so it keeps the PCB a lot simpler and smaller. Leave your comments below, but what I'm going to do now is I'm going to just double check this circuit still works off of the DC supply, and I can find out what I've done with my leads. So that goes to positive, negative is just sitting over here. I had a negative there, I'll disconnect that. Negative connects to there. Disconnect the loads disconnected. Yep, we still have an output. Although the meter must have reset at some point. There we go. Still got 5.1 odd volt on the output as where it was set before it blew up. Well, not, the circuit didn't blow up. The PSU blew up and then took out the 12 volt winding on that side. Which is, yeah, okay. As I say, it probably exceeded 5 amps. Anyway, leave your thoughts down below, and yeah, I'll get on to that. I'm going to pack this up now because I've got other things to do on the channel. I've got a couple of repairs coming up now. I need to finish that other power supply in the background. That'll be finished sometime this week. And yeah, so I'm going to leave this video here. If you enjoyed it, please remember to rate, comment and subscribe below. And this is the Astro 30 as always saying see ya. Thanks, have a great day.
Because